Parents need descriptive recipe titles. If we recommend recipes from a database with names like Mama's Veggie Mix, parents won't know what's in that. If we recommend single ingredient recipes only, we won't have the variety to actually provide meal recommendations that can address all possible nutrient gaps after the first meal scan. We need recipes like pasta with mozzarella and cherry tomato that collectively have a lot of nutritional variety. Mozzarella provides calcium, cherry tomato provides potassium. We also need recipes in our database categorized as protein, starch, or veggie. We need this because we're going to create an algorithm that finds the best combos of protein, starch, and veggie based on the nutrient gap for the scanned meal within 5 to 10% error, which is well below any risk of toxicity for these naturally occurring nutrients. This way, we can present a meal plan that solves every nutrient gap against daily value, which is the scientifically recognized standard for iron, iodine, potassium, and all our track nutrients. As for changes, we can preset the meal plan and let the parent change things. The parent may say, I don't want chicken tonight, I want salmon. I'm serving green beans today, not peas. When they change something, the algorithm determines if we need to add a snack or do something simple to compensate for the change. The plan always gets all 11 nutrients to 100% daily value to support focus, memory, coordination, emotional control, and mood stability. So, our first step is finding a recipe database that's free. I found a number of APIs and great databases that have refined recipes parents will recognize, but we need to pay them significant money to either get the database in full or we have to pay as we go. So I found an open source recipe database. It's messy and it carries a lot of duplication, but it carries these attributes for each recipe record: title, directions, and a list of ingredients. It contains 2 million recipes, and that's the kind of scale that we want to think about when we consider constructing an algorithm that can find the right combo of subsequent meals to our meal scan and that can get the child to 100% daily value for all nutrients. So we're going to go ahead and download this database.
Once it was downloaded, I worked with Gemini to create JSON scripts that would help us identify all the recipes that actually serve our purpose. After uploading these 2 million records to an AWS DynamoDB table, I worked with Gemini to create a JavaScript workflow that would score these 2 million recipes against our criteria for inclusion in our app. I created a Gemini prompt that asks Gemini to score recipes from 1 to 10 on a series of attributes that include whether or not the recipe is kid-friendly or prep time is under a certain number of minutes. There are other attributes as well, which I won't go into. But Gemini is smart enough to make a directional determination here and reflect that directional determination through a score of 1 to 10. So the scoring works in 2 steps. I create a new file with a new structure. Let's take a look at the structure in the terminal. Each entry in the new file has an attribute where we store a copy of a unique recipe record, and then another attribute where we store our Gemini prompt. Why did I do it this way? Well, having the Gemini API read a prompt and hold that context while reading 2 million records, then provide 2 million scores is impossible. It will forget. It will hallucinate. But having the Gemini API reread the prompt every time it processes a record means it treats each of our 2 million recipes like a unique problem it solves and only has to hold prompt context for one record at a time. I just make sure that prompt is exactly the same for each record, and after testing, I found that the scoring from Gemini was consistent across all our records. So the first step of scoring is generating the new file with each JSON record containing an attribute with our prompt text and the other attribute containing our recipe record. That's what you see on the screen, input manifest. On the top record, you see the text: you are a specialized nutritionist for the Sprout Brain app. Score each recipe from 1 to 10 on, our scoring attributes. And then under that, you see text and an ID number, and then you see a title for a recipe, which is cocktail, barbecue, something or other. List of ingredients, which includes grape jelly, and barbecue sauce, and then a list of instructions. That is the raw recipe entry from our database. And so I constructed this file where we have both in the same record. We have the prompt, and then we have the actual recipe record. And the second script is going to go in with the directions to read the prompt, send the prompt to Gemini along with the recipe record, and get a response for each record for each of these. We'll call this set of two elements here one record. So it's reading the prompt every time, reading the prompt and the recipe every time, so that it's not losing context by reading the prompt once and then trying to do this 2 million times while memorizing the prompt. So hopefully that's clear. Yeah, the second step is actually sending the record to Gemini with instructions to read the prompt in each record. Right, so very quickly we're going to go and take a look at that file. This is run tier 2 speed Gemini. It's a Python file, and this is the file that's responsible for actually taking our input manifest file and converting it into a scored recipes file. Carries all of our recipes with a score from 1 to 10. We're going to scroll down here and take a look at our line 27. We're already there. Score recipe function. This is the recipe where we actually, do the scoring. And then I'll just show you very briefly sort of how I ended up coming up with this. And I have a discussion with Gemini going back and forth on tuning this for memory as well as staying under our rate limit for the Gemini API. Decent back and forth with Gemini about this. So you see the memory issue. We had an issue with a 3 gigabyte file, streaming input. So trial and error making this work. And as a non-developer working with Gemini to get this script functioning and to get our 2 million records read through the Gemini API. So let's pause the video here. We're going to take a look at the process, or at least the end of the process, for scanning all 2 million records with Gemini, or sending all 2 million records with Gemini and getting a score and response back, and then we'll proceed. Is for the last 20 hours since yesterday afternoon. We have been watching as each of these records has been sent to Gemini with response back. As they're sent back with their response, we get a progress indicator based on the because I put this logging in the file. So right now we're up to almost 2 million out of 2.2 million. So 1.9 million out of 2.2 million. We've only got 2.5 hours left, 2.3 hours left. A big part of making this work is making sure that our requests per minute stays under what's allowed for Gemini API Tier 2. Initially, we had concurrency around 400 because we had higher latency, and then we added a number of things in here to improve speed. Let's see. Yes, thread pool executor. So we created this loop to make sure that each of our requests can actually run simultaneously. We imported this app sync, or this async IO and thread pool executor, and async IO has an automatic limit. So it was using about maybe 25%, 50% of our concurrency limit all at one time. And even when we were running 400 or 150 at concurrency limit, only about 50% of that or less was actually running, and our latency was about 45 seconds a record, which was going to make this take days. So what we did was we added thread pool executor and reduced the concurrency limit, and actually reduced our time down to about 1 second, 1.5 seconds, 1.2 seconds. I think it's the lowest that it's gotten. for each record. So we were able to complete this within a day, which is frankly amazing. Sending 2 million records to Gemini for it to perform a qualitative analysis on what they're doing and for it to send back a score that represents that qualitative analysis is phenomenal. On the right here, what you see is actually a sample of the data coming back. So you will see for each of these a score here. So this recipe is yeah, this is our score. This recipe is under this ID number, and it has its title, which is stored in our recipe data. But Gemini is basically saying for recipe ID, whatever, it gets a score of 7 on our scale of 1 to 10 for parent friendliness. This one gets a score of 2, right? And what we think about is it's probably not kid-friendly ingredients. Oysters, it includes oysters. Most kids don't like oysters. Most parents don't want to serve oysters to their kids. So oysters are not generally kid-friendly due to texture. Prep time is moderate, but the recipe includes alcohol, cognac, right? Again, who's who's doing that for their kids Wednesday night, serving oysters with cognac? Now, I want to try that recipe, but the kids don't want to try that recipe. And ingredients that may not appeal to children: green peppercorns. The nutrient density is decent with protein from oysters, but overall the recipe is not very parent friendly. So it's doing its job. This one got a 6. Prep speed is moderate. Let's see if it lists any of the ingredients. It's decent due to the cheesy flavor, but texture may be challenging for some. Nutrient density is moderate. Cheese provides calcium and protein, but the recipe is high in fat and low in fiber. So this one probably failed our nutrient density or nutrient quality score here. Okay, this one, prep time is good. However, the recipe contains spice and potentially unfamiliar flavors, textures for children. So it's done this 2 million times, or almost 2 million times. And within 2 hours or so, we'll have a full database or a full data set, 2 million records, each scored this way. And the plan is to create a distribution from that to see how many are ones, twos, threes, fours, fives, sixes, and really our focus is going to be on 8, 9s, and 10s. And if any of those subsets are around 50,000, then we have gotten a set of recipes that we can evaluate. Okay, great. Now we have our 2 million records scored on our criteria for inclusion. Let's look at the terminal. So I wrote a command and teed up a couple of full scored records. So let's look at a few. We have overnight oats, which is a score of 9. Quick prep, so that's a great score, right? 9 out of 10 is phenomenal. Quick prep, kid-friendly flavors, contains protein, fiber, and healthy fats. And these are the ingredients. We have a raw vanilla milkshake, score of 8. Quick prep time, kid-friendly flavors. Let's see what else we've got in this little sample. And it's definitely important with Gemini, if you're doing some kind of qualitative scoring like this, to make sure that the you have a reason field as well. Have Gemini tell you why it's doing what it's doing, because in some cases your prompt may not be specific enough. There may be things you haven't thought about, and it's going to give you some feedback. If there's scores that you're not pleased with, you can use that feedback to retune the prompt. Of course, you would also want to be able to view this before your process is complete, right? We don't want to wait a whole day to get 2 million of these back and find out we messed something up. So, but this reason field is essential. So, score of 8, raw vanilla milkshake. Score of 8, double choco chia banana muffins, right? Zucchini oat bread is also score of 8. And pasta with pesto, potatoes, and green beans, score of 8. Fast prep, familiar pasta shape. Pesto can hide the green. We love that, right? We love recipes where we're hiding things that kids might not eat themselves individually, but we're putting it in something that they really like. Potatoes and nutrients, good balance overall. And then they've got granola bars here. Now, are each of these things that we definitely want to include? Overnight oats, probably for breakfast, or even as maybe part of a dinner option, but definitely breakfast. That's really good, right? Vanilla milkshake, maybe a snack. Raw vanilla milkshake, almond milk, vanilla, bananas, low potassium day. That could be useful. Double choco chio banana muffins, less likely, right? This is the kind of stuff where it's a subjective name, or it's a name it's designed to get the recipe views for people who are looking for a spectacle for, a spectacle recipe or something exciting or interesting. But for a place where we're recommending recipes in tandem or together, we will probably exclude this later on. Zucchini oat bread, that's zucchinis. We definitely want that, but zucchini oat bread, this might be a little obscure. So there's still gonna be things that there's still rounds of filtering that need to take place after this. But you see the fact that we have all of the recipes that we have now are quick prep time, easy flavors kids would be interested in, and relatively kid friendly means that we've eliminated, millions, literally millions of recipes that were not this way, and that's very very helpful. Pasta with pesto, potatoes, and green beans. This is a phenomenal candidate, right? You could see a parent choosing this to include in meal prep or dinner for the evening. 3 ingredient granola bars, less likely. Most people just buy granola bars, but again, this is a better set of recipes to work from. Let's see. Okay, so now we need to know how many records we have for each score so we can see what slice of recipes we should cut and which we should keep. We're aiming for no more than 50,000 to 100,000 recipes because that's about as many as we can possibly store in our app cache at once. So I had Gemini, again, create a memory safe distribution script that gives us the count of recipes for each score. And what I found is that we have enough from score 8 to 10. So I wrote a script to grab recipes scoring 8 and above only and put those in our elite parent recipes.json. So that file is going to be in our VS Code, and we're going to go and find it here. Elite recipes. You're going to get a chance to see a little bit into the future, but elite parent recipes.json, and there's still way too many records for this to demonstrate on its own, but you can see that, or for this to you're going to get an error message about this, but you can see we've got all of our recipes here: turkey ragu, baked chicken taquitos, pasta with pesto potatoes, quick chickpea and summer vegetable stew, taco soup. These are things that are a little bit more in line with what we're talking about. And so what we need is what we've got is about 50,000 or so recipes, all in I believe this is 51,000 recipes, all in this particular file. And we can use this to advance our pipeline. Okay, great. Now we have our 2 million records scored on our criteria for inclusion. Let's look at the terminal. So I wrote a command and teed up a couple of full scored records. So let's look at a few. We've got, we have overnight oats, which is a score of 9. Quick prep, so that's a great score, right? 9 out of 10 is phenomenal. Quick prep, kid-friendly flavors, contains protein, fiber, and healthy fats, and these are the ingredients. We have a raw vanilla milkshake, score of 8. Quick prep time, kid-friendly flavors. Let's see what else we've got in this little sample. And it's definitely important with Gemini, if you're doing some kind of qualitative scoring like this, to make sure that the you have a reason field as well. Have Gemini tell you why it's doing what it's doing, because in some cases your prompt may not be specific enough. There may be things you haven't thought about, and it's going to give you some feedback. If there's scores that you're not pleased with, you can use that feedback to retune the prompt. Of course, you would also want to be able to view this before your process is complete, right? We don't want to wait a whole day to get 2 million of these back and find out we messed something up. So, but this reason field is essential. So, score of 8, raw vanilla milkshake. Score of 8, double choco chia banana muffins, right? Zucchini oat bread is also a score of 8. And pasta with pesto, potatoes, and green beans, score of 8. Fast prep, familiar pasta shape. Pesto can hide the green. We love that, right? We love recipes where we're hiding things that kids might not eat themselves individually, but we're putting it in something that they really like. Potatoes and nutrients, good balance overall. And then they've got granola bars here. Now, are each of these things that we definitely want to include? Overnight oats, probably for breakfast, or even maybe as maybe part of a dinner option, but definitely breakfast. That's really good, right? Vanilla milkshake, maybe a snack. Raw vanilla milkshake, almond milk, vanilla, bananas, low potassium day. That could be useful. Double choco chio banana muffins, less likely, right? This is the kind of stuff where it's a subjective name, or it's a name it's designed to get the recipe views for people who are looking for a spectacle for, a spectacle recipe or something exciting or interesting. But for a place where we're recommending recipes in tandem or together, we will probably exclude this later on. Zucchini oat bread. That's zucchinis. We definitely want that, but zucchini oat bread, this might be a little obscure. So there's still gonna be things that there's still rounds of filtering that need to take place after this. But you see the fact that we have all of the recipes that we have now are quick prep time, easy flavors kids would be interested in, and relatively kid friendly, means that we've eliminated, millions, literally millions of recipes that were not this way, and that's very, very helpful. Pasta with pesto, potatoes, and green beans. This is a phenomenal candidate, right? You could see a parent choosing this to include in meal prep or dinner for the evening. 3 ingredient granola bars, less likely. Most people just buy granola bars, but again, this is a better set of recipes to work from. Let's see. Okay, so now we need to know how many records we have for each score so we can see what slice of recipes we should cut and which we should keep. We're aiming for no more than 50,000 to 100,000 recipes because that's about as many as we can possibly store in our app cache at once. So I had Gemini, again, create a memory safe distribution script that gives us the count of recipes for each score. Okay, and so this is our script that goes through our scoring or our scored recipes JSON, and it tells us how many records are in each score, right? Or how many records have a certain score. So we have 43 records scored 10 out of 10. 4,836 records scored 9. 47,112 records scored 8, and then we have 487,000 for 7, 572,000 for 6, and 275,000 for 5, then 400,000 for 4. So follows kind of like a bell curve, skewed towards the back. Obviously, we're not interested in recipes that scored 1, 2, or 3. We've visually ID'd. A lot of those recipes have issues. Either they're obscure ingredients, or they take too long to cook, maybe too many ingredients, all the stuff, all the good reasons we excluded. And this is when we think about what we just talked about, what we just mentioned with looking for a cutoff that allows us to have about 50,000 recipes. This is almost perfect because 8, 9, and 10 give us in total about 51,000 and change recipes. So that's great. Tab recipes scoring 8. and above only, and put those in our elite parent recipes.json. So that file is going to be in our VS Code, and we're going to go and find it here. Elite recipes. You're going to get a chance to see a little bit into the future, but elite parent recipes.json, and there's still way too many records for this to demonstrate on its own, but you can see that, or for this to, you're going to get an error message about this, but you can see we've got all of our recipes here: turkey ragu, baked chicken taquitos, pasta with pesto potatoes, quick chickpea and summer vegetable stew, taco soup. These are things that are a little bit more in line with what we're talking about. And so what we need is what we've got is about 50,000 or so recipes, all in the, I believe this is 51,000 recipes, all in this particular file. And we can use this to advance our pipeline. Okay, great. So, we've got the recipes. But if we look at our recipes again and actually read the instructions this time, we're going to notice something that's going to present a challenge for us going forward. Let's look at this one for the zucchini oat bread. Skin and slice a medium zucchini, chop in a food processor, add all other ingredients, blend until smooth. Add some or all curants by hand, stirring if you don't want them blended in. Pour into muffin cups or well-greased loaf pan, etc., etc. What do we notice about this? We want to use these ingredients. Eventually what we want to do is give each ingredient a nutrient density for each nutrient, and then we want to add that up and have our nutrient contribution for the entire recipe, right? At whatever amount that whole recipe makes, and then we can divide that by, whatever amount we intend to put in a serving. But to do that, we need a proportion of how much zucchini versus how much yogurt versus how many oats versus the rest of this. And we don't have it. We don't have quantities or units on certain items, and that's what we need to integrate these recipes into our database, into something that can into functionality that works with an algorithm, right, or into an algorithm itself. So we need to fix that. And so what I did was I created a script that batches our 50,000 recipe records that look like this on the left into groups of 5. And our prompt in this script instructs Gemini to return the exact same recipe object, but for ingredients. Add realistic home cooking quantities to each ingredient in the ingredient array, then insert approximate quantities based on the recipe name and ingredient components. So we're not going to get into exactly how I wrote that script, but after testing, our output becomes elite recipes rewritten final. And now let's go and look at those, or see if we can grab a group of those. Just get the name from my JSON file here. Okay. Okay. That's the problem, isn't it? We need the file extension. Otherwise, this isn't going to work. So as a non-developer, this kind of thing happens. So I'm going to go back into my Claude and get Claude here to rewrite this for me. We'll see if this version works. There we go. Okay. So now what you can see is after I ran the script to add quantities, I added a quantity field in the actual ingredient object. And so for this one, pasta, potatoes, pasta, pesto, potatoes, and green beans, we had previously we just had ingredients: potatoes, salt, cavatappi, green beans, and pesto, right? Now we've added quantity, unit in pounds, quantity, unit in tablespoons, quantity, unit in pound. So I can do math with this, right? I can say, okay, the recipe calls for all these things. Once I have nutrient densities associated with potatoes, then I can multiply or divide my nutrient density for the ingredient. Well, let me back up a second. I can take the nutrient density for, give each of these ingredients 11 different nutrient densities, right? So iron, iodine, calcium, potassium, the same for all these ingredients. They each get their own. And then what I'll be able to do at some point with that nutrient density is use this quantity to help us create a weighted sum of every nutrient density based on what the ingredient nutrient densities are and what their quantities equate to as a proportion relative to each other. So this is very, very important. So glad we got that done. Now it's time to make this list of recipes compatible with our algorithm concept. And the recipes need accurate nutrient densities in milligrams per 100 grams for iron, iodine, calcium, choline, B vitamins, omega-3, magnesium, potassium, zinc, fiber, and everything we track. Remember, all recipes came with an array of ingredients. So, the same array we were just talking about that you see here, which is now augmented with quantity and unit, it came with an array of ingredients. So what we're going to do is write a script to extract all unique ingredients from our recipes. We're going to extract potatoes, extract salt, extract green beans, extract pesto, and we're going to put those in a file. Then we're going to send each recipe over to the USDA API, which will respond with iron, iodine, calcium, choline, B vitamins, omega-3, magnesium, potassium, zinc, fiber, all their densities for every single ingredient item. We're then going to go back to our recipe records and augment their JSON object with a list of ingredients. Augment the list of ingredients. And in that list of ingredients, we're going to augment it with our nutrient density for each nutrient for each ingredient. So if my recipe has chicken, flour, and garlic, I'm going to have a list of ingredients, including those items. They already have their quantity and unit attached since our last exercise, since our last script. But then for each item, I'm going to also store that particular item's nutrient density for each of our 11 nutrients. So in total, I will have 11 nutrient densities for chicken, 11 nutrient densities for garlic, 11 for flour, all stored neatly in our recipe record. So right now we're going to take a look at our unique ingredients file. Move through our VS Code here. And so this was the file that we created with the most recent script, or the script after the quantity adding script. There's a new script that I ran, and that script just separates out or pulls out all of our ingredients from all of our 50,000 plus recipes. And we see here garlic, and we see a recipe count, right? It's in 11,697 of our recipes. It gives us a few samples just so that we can be sure that it's pulling correctly from the data. And in this script, we create data object for USDA ID, USDA name, match indicator, and our nutrients, and set each of those to null. The reason that we're doing this is the record that eventually we're going to pass to the USDA API. It's a free API that provides nutrient information, and we're going to have that API populate, or we're going to take the API response and populate these nutrient fields, which you can see one for iron in milligrams, one for iodine in milligrams, calcium in milligrams, omega-3 in milligrams. There is going to be a need to convert a couple of these. So iodine, for instance, is actually frequently stored in micrograms. But if we know, as long as we know what the factor for conversion is, we can troubleshoot this. We're probably going to run multiple audits since this is directly correlated with the accuracy of our app. But this is how we're bringing the information in, and we are getting it from a reliable source in the USDA API. This is the JSON that I created. So next we're going to take a look at the USDA lookup file, which is the actual script that we're going to use to send these records to USDA, to the USDA API, get a USDA ID, and then retrieve our milligrams. So this is what that file looks like. This is the file. And line 14, let's go back to line 14. That's where we map the USDA nutrient code for the nutrients that we're interested in, which is obviously key, right? So we have USDA codes for each of these nutrients. This is how the USDA website, and you can see the site here, maps the nutrient densities that we're interested in. So iron is 1089, calcium is 1087. And then we can scroll down to line 249. That's it. That's the end of the files. So good. After running this, I'll have my nutrient densities for each nutrient, and then we can bring everything together. Okay, so after running our script and getting all of our individual ingredients over to the USDA API, we got responses. And it took about a day. I actually had to split my ingredients into 3 different files, and then use 3 different API keys. They're all free, or at least the use of that is free. And it returned information here. So we have for onions, iron milligrams per 100 grams. That's the standard. It doesn't say it here, but everyone knows that it's per 100 grams. Calcium, 23 milligrams. Magnesium, 10. Potassium, 146. Of course, you're not going to serve 100 grams of onions, but the factor of 146 milligrams per 100 grams is what we're going to use when we calculate the total potassium in a recipe, which will include onions. Garlic, we have all of our data here. Tomatoes, obviously that's a big one, and it comes in. Some of these are not completely accurate, and so there are going to be, or there were, multiple rounds of edits and audits and edits in the correct order to get these right. But baseline wise, a good majority of these are correct, and it left a lot less work for us to do on the auditing side. Let's see here. I also had to end up getting calorie densities for all of our nutrients as well, with a similar process, and that's in a separate JSON file here. Calories, well, it's actually the same. It's ingredients, right? And then I augmented each ingredient with its calorie density, calories per 100 grams. And we're going to use that in our calculation as well, because if you remember, we're creating recipe recommendations for kids, and we have the max stomach capacity and min max calorie range according to USDA. So if we're calculating a meal, if we're creating a meal and in the process of doing that, we need to calculate not just whether or not it's nutrient dense enough, we need to understand the calorie burden as well, so that we're not producing meals that are super nutrient dense, but 600 grams when the child's stomach can only handle 300, right? Or something ridiculous like 1,000 calories when the max for a 7-year-old or 8-year-old is much lower than that. So we have this information here, and now we're going to go to our phase 5, because everything I mentioned up to this point amounted to phases 1 through 4. We just didn't name all of our files with that naming convention. But so now we're going to go to not the phase 5 JSON, but our actual phase 5 code. Here we go. And with Gemini's help, I wrote this script that ultimately will bring all of our ingredients and their nutrient densities per 100 grams into the recipe objects where they're included. The purpose of this is to add the nutrient density for each ingredient to each recipe object. So we will also convert our ingredient quantities like cups, teaspoons, etc. into grams. So our recipe objects have each ingredient with 11 nutrient densities and grams used for each ingredient, which we derive from our quantities. Now you can see why quantity was so important to add. Let's go, here on line 132. This is where we gather the ingredients and their nutrient densities and augment our recipe objects with that information. And then let's go back over to our terminal screen. So I'm going to show you now what the result of phase 5 was. So let's just check and make sure you can see. Yes, you can. So now we have overnight oats again. Remember that recipe from our previous example. We cleared out the genre and the label because that was actually bad data from the original database. But what we have is instructions augmented with our actual quantities. And then we have our ingredients with our quantities. And then we have our grams based on what the instructions say, in terms of its quantity. 0.5 cup amounts to 120 grams. And then what we have is our nutrient densities for each ingredient. So oats, these are the nutrient densities for oats. Greek yogurt, these are the nutrient densities for Greek yogurt. Nut butter, these are the nutrient densities for nut butter. All of that is here in one record. We're bringing all that together. Let's see here. So now we've got 51,000 records like this, and that's really powerful. So in the next step, we're going to go to phase 6, and let's go back over to our VS Code. And in phase 6, you will see the script that we wrote here. So now we can really wrap everything together. We're going to multiply our grams for each ingredient by our nutrient density for each ingredient to get our nutrient contribution for each ingredient for the recipe. So all along, all 11 nutrients, right? So we're going to take the grams used for each ingredient in the recipe and multiply each nutrient density for that ingredient by the number of grams divided by 100 grams. This will give us the nutrient contribution for each nutrient on each ingredient in a particular recipe. So now we will use the same grams to give us a weighted sum for all the same grams per ingredient, right? This ingredient had 2 grams, this ingredient had 100 grams, whatever. But it's all standardized in grams. And that will give us a sum for all nutrients across all ingredients. That will be the nutrient contribution for the whole recipe. So for example, we had an ingredient beef with 2.5 milligrams per 100 grams of iron. For every recipe object that uses beef, we will multiply that 2.5 milligrams by the ingredient quantity in grams as a fraction of 100 grams. So now for each ingredient in each recipe, we will have the total nutrient contribution in milligrams for iron. At the end of phase 6, we should have this for every recipe in our 50,000 recipes. So let's check this out in our terminal. back here over to our phase 6 piece, right? And what we have is what we discussed, right? So let me find the actual record. Yes, overnight oats again. And we see we have our name, our quantity, our grams. Then we have nutrients and nutrient density for this particular ingredient, right? But then we have a new element called nutrient contribution. And so that's what we calculated in phase 6. We used these nutrient, this nutrient density, which is per 100 grams, and then we multiplied it by the number, the factor effectively of 100 grams that we actually use. So remember, with iron, we used a little bit over 120 grams. This is per 100 grams, right? 4.25, it's 4.25 milligrams of iron per 100 grams. So considering the fact that we're using 120 grams, 5.1 for the nutrient contribution makes sense. This is the actual nutrient contribution for oats, given the quantity of oats that we have, and the nutrient density per 100 grams. Given the fact we have 120 grams, we are getting 5.1 milligrams of iron in a full quantity of this recipe, or a full batch of this recipe. We're getting 5.1 milligrams per 5.1 milligrams for the whole thing of iron, because we know 4.25 milligrams for every 100 gram times 120 divided by 100 is 5.1. So we do this for all of our records, and then the other piece that we did in this file as well is we added up. We created a weighted sum and added up all of our nutrient contributions at the ingredient level. We added all of those up to generate our recipe nutrient contribution, which represents, here we go, for the entire recipe, how much iron, how much calcium, how much magnesium, how much potassium. Mind you, this is not a serving size. This is for the full batch that the recipe makes. But this math is for a recipe size, which now we have equated to a gram amount for the entire recipe and a calorie amount for the entire recipe. So in our algorithm, we can split and manipulate this recipe so that we can get an amount that is tuned to give us however much iron or however much calcium. We can also search these recipes for recipes that have a certain nutrient contribution, and then can be plugged into our meal plan. So this is extremely valuable. This is exactly what we need. We have a traceable pipeline that gets us to nutrient contribution for 11 nutrients for 50,000 recipes, and that is going to be essential to the working principle of our algorithm. Cool. So one last thing, when I looked at our recipe names through a number of audits, I found that there were quite a few duplicates or near duplicates, things like chicken noodle soup and chicken vegetable noodle soup, right? Virtually the same thing. And so I wrote a script with Gemini to look for noise words, as well as create a Jacquard function here that determines similarity. Basically, if there's we split a recipe title into tokens, and if the shared tokens are above a certain threshold, in this case I think it was 70%. If 70% of, here it is, clustering at 70%. If we have more than 70% similarity, then eliminate the second record, right? So we wanted to eliminate duplication. So I'm going to write a terminal command now that, or paste one, that actually tells us how many records we could eliminate or eliminated during deduplication. And look at that, 51,489 records down to 26,737. So half, half of our database was duplicates, or half of our database candidates were duplicates. There are lots of tools out there that can help you clean data quickly, and I will say that in this case, working with Gemini has made not just discovery, but synthesis of different concepts much faster. I'm familiar with this concept, but as far as putting it into code and doing it quickly, Gemini accelerates the process, and Claude as well. A lot of this pipeline was done with Gemini because this was prior to, I did a lot of this work prior to really discovering Claude Code and working with Claude, but it worked out either way. So that's good. We've gotten rid of our duplication. After that, the result of that was a new file called Elite Recipes Phase 6 dedupe. And then beyond this, there's only one more step. So remember, we were supposed to present 3 types of recipes, right? 3 categories. The genre field in our database was complete junk. There were things listed as snacks that were actual meals. There were things listed as meals that were snacks. That was not something that we could use at all. So every meal that we recommend has to have an accurate protein, an accurate starch, an accurate veggie, right? So we're going to write, or we did write, a Gemini script to categorize each recipe as protein, starch, and veggie. And we'll also have combination categories. So we have protein, starch, and starch and veggie as their own categories, because you have dishes where it's it's mixed with proteins and starch. For instance, spaghetti would be a mixture in technical terms. Spaghetti with lots of meat, spaghetti with meatballs. But our app is going to primarily use our protein, starch, and veggie. We may have the flexibility to kind of swap in combo recipes as necessary. So we may do a hybrid slot where if it's protein and starch, then it fills both. But we need these categories for our algorithm to function. So our final script is going to send 26,000 recipes to the Gemini API to read each recipe and categorize it in an augmented field called category. So our end result is going to be a file called Elite Recipes Phase 6 categorized.jsonl. And if we run the terminal command to get the count from the file, we should have just over 26,000 records. Before we do that, let's actually look at the file itself, look at the output from the file itself. Okay, so we're back here in the terminal. We're going to paste our piece here, and the recipes that come up are all now categorized as veggie, because I asked specifically in the terminal command. I just prompted to get 3 recipes that are essentially that are categorized as veggie. So once we scroll past our actual ingredients, right, this has broccoli florets in it. We're going to go up to see the title, and we see easy gingered vegetables, right? So we've got everything that's in this recipe. We've got our instructions, we've got our nutrient densities, but we have it categorized as veggie. This next one categorized as veggie. So I can also do the same thing where they are categorized as starches. And remember, we still have to audit the names, right? So like easy gingered vegetables is not descriptive enough to appear in our app. But we've got a good nutrient dense, diverse vegetable option that has all of the infrastructure required for our algorithm in the record, ready to go. Starch, right? So this is another set of 3 recipes. This time these are starches, and let's see which ones it gave us. So orzo with parmesan and basil, right? That's great. That's a great example of something that we want to appear in front of parents. We may say orzo pasta, if orzo itself is a little bit obscure for certain folks, but like easy over fries, right? These are French fries, potatoes, right? Nutrient contributions from potatoes are factored into our total recipe nutrient contribution. All of this is in a single record. So we've covered a lot of ground, made a lot of progress. We still need to clean this manually, right? And probably only start with starches and veggies. Protein, we, recipe-wise, searing salmon, baking it, that doesn't necessarily make a difference. But these starches and veggies that have combinations of things are very, very useful here in constructing our meals. We're going to need to focus on cleaning those. And there's thousands of those total. But with our accelerated script writing ability, we can recategorize or delete recipes that are messy or still not relevant using keywords or worst case, individual recipe IDs. But our database is constructed. It may not be complete yet, but we have a solid foundation that we can use to move forward.